Welcome back to section 2. We're going to apply the octet rule and draw Lewis electron dot structures for simple molecules and polyatomic ions. Gases in our atmosphere like oxygen gas, nitrogen gas, water, carbon dioxide, common fuels like methane, ethane, propane, and most of the compounds in your body are compounds that have covalent bonds. Covalent bonds are also responsible for the atom-to-atom connections in polyatomic ions like carbonate, cyanide, ammonium, nitrate, and phosphate. We will develop the basic principles of structure and bonding using these and other small molecules and ions. But the same principles apply to larger molecules, from aspirin to proteins and DNA, with many thousands of atoms. The molecules and ions just mentioned are composed entirely of non-metal atoms. A point that needs special emphasis is that in molecules or polyatomic ions made up of only non-metal atoms, the atoms are attached by covalent bonds. Conversely, if there's a presence of a metal in a formula, it's a signal that the compound is likely to be ionic. The electron pair bond between the two atoms of a hydrogen molecule is represented by a pair of dots or a line. So notice that I have hydrogen that has one dot, another hydrogen has a dot, and when we form that bond, we can do it like this, we can do it like this, where the first hydrogen has the top dot, the second hydrogen has the bottom dot, so we can see that there's a pair. Or we can have a line representing those two electrons. We kind of visualize that one hydrogen has a dot there and the other hydrogen has a dot there, and we just connect the dots. Fluorine, F2, each has 7 valence electrons. We can see that one fluorine has a lone dot there, another fluorine has a lone dot there, and they pair up here to have our bonding pair. We can show it like that, or we can show it as a line. That line can be called my bonding pair. And then there, notice around those fluorines, there's 2, 4, 6 lone pairs around each fluorine. They are not involved in bonding, so they're called non-bonding electrons. We can also have multiple bonds. Before, over here, hydrogen just had a single bond, fluorine just has a single bond, but we can have double bonds and triple bonds. Carbon dioxide and dinitrogen, or just nitrogen gas, are examples of molecules in which two atoms share more than one electron pair. In carbon dioxide, the carbon atom shares 2 double bonds with each oxygen. The valence shell of each oxygen in the CO2 has 2 bonding pairs and 2 lone pairs. Let's look here. I've got 2 lone pairs and 2 bonding pairs. In nitrogen, the 2 nitrogen atoms have 3 pairs of electrons, so they're linked by a triple bond. So each nitrogen atom has a single lone pair. If you look at each nitrogen atom, that's 2 electrons, 4, 6, 8. And then this nitrogen on the left has 2 in the lone pair, 4, 6, 8. So there is still an octet of electrons around each nitrogen atom. We could look at the same for the oxygen on the left here. If I circle this, this would be 2 electrons, 4, 6, 8. The carbon, there would be 2, 4 in that double bond, 6, 8 in that double bond. And this oxygen on the right, we would have 2, 4 in that double bond, 6, 8. The octet for each atom is being met. Let's look deeper into this carbon dioxide. To draw a molecule, I know it's easy to look at that dot diagram and be like, what? How did that happen? Well, first we need to figure out how many valence electrons we need to account for anytime we're drawing a compound. Well, you look at your periodic table, carbon has 4 outermost electrons, so 4 coming from carbon. And oxygen, put your finger on it, would have 6 outermost electrons, and there's 2 oxygens. So 6 times 2 is 12, plus 4, there's 16 electrons that we need to account for when we are drawing this compound. So let's start with C, and then there's 2 O's. We're going to have O's around that C, just like that. And let's connect them by 1 bond. So that shows 2 electrons, 4 electrons already. But we need 12 more electrons around these. And plus, it's not meeting the octet rule. Right now, the oxygen on the left only has 2 electrons. We need it to have 8. This carbon, notice there's 2 and then 2, so it only has 4 electrons around it. And then the right oxygen only has 2. So octet is not being reached. What I like to start doing next is to start filling in electrons to get to 16. Let's do that. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right, let's look a little deeper at each of these elements. This oxygen is happy. He has 2, 4, 6, 8. Cool. Let's look at the other oxygen. He is happy. 2, 4, 6, 8. Okay. Let's look at my carbon. My carbon only has 2, 4 electrons. It does not have an octet. It wants 8. So we need to share some electrons from those oxygens. Right now, carbon only has 4. It needs 8. So let's take 2 from this one oxygen and share it. So that carbon and oxygen will share those 2 electrons. So I'm going to scribble these out since I moved the electrons that were on top of that O2 sharing with that carbon. Now look, I didn't take them away from the oxygen. If I look at oxygen, I have 2 on the right, 2 on the bottom, and because of this double bond, that's 4. So that oxygen still has 8. But this carbon, because of sharing, this carbon has 2, 4, 6. Oh, it still needs 2 more. So let's take 2 from this oxygen. And it could have been these 2, those 2. It doesn't matter. I'm just taking the 2 on the top and I'm going to share it. Instead of being only in the oxygen, let's share with the carbon. So we'll have a double bond here. That means that those are gone because we're sharing with that carbon. Now let's do a quick count. My oxygen on the right has 2, 4, 6, 8. My carbon has 2, 4, 6, 8. And this oxygen has 2, 4, 6, 8. And let's just do a quick count to make sure that we have 16 total. 2, 4, 6, 8, 10, 12, 14, 16. And that gives us our CO2 structure, and each oxygen has 2 lone pairs around it. Doesn't matter where those lone pairs are when we're drawing our Lewis structure. Sometimes it's difficult to figure out where that central atom, sometimes it's difficult to figure out who that central atom is going to be. Generally, it's the one with the lowest electronegativity. We're going to read more about electronegativity in section 7. The highest electronegative element is fluorine. So electronegativity increases as I go to the right and as I go up. So if you look at fluorine, put your finger on the periodic table, number 9, that is the highest. So in the halogens, it's higher than chlorine and bromine. So it gets higher as we go up. And fluorine is higher than boron, carbon, nitrogen, and oxygen. So it gets higher going to the right. So if I looked at CO2, for example, and I said, which one is the lowest electronegativity? So which one is furthest from fluorine? Carbon versus oxygen. The carbon is furthest to the left, and it's not down, it's in the same row. But if it was further down and left, it's going to be the lowest electronegativity. For simple compounds and ions, usually the first atom in the formula is the central atom. It's not always the case. There are some exceptions like water, H2O. There's only one O, that's the central one, and 2 H's around it. Certain elements often appear. Carbon, nitrogen, P, and S often are the central atoms. Halogens, the fluorines and chlorines, are often the terminal atoms because they form a single bond. Oxygen is a central atom in water, but combined with others, it's usually not the central atom. And then with rare exceptions, hydrogen is never a central atom. It's usually always attached as a terminal atom. Let's draw the Lewis structure for NH3. So we've got nitrogen is our central atom. Again, it's listed first. We're going to go with that, and there's 3 H's that are going to be surrounding it. Let's figure out how many valence electrons we're dealing with. Nitrogen, found on the periodic table, has 5 valence electrons. Each hydrogen has 1, so we're going to do 1 times 3, so that's 3 plus 5, so we have 8 electrons that we need to show. I'm going to draw my N, and I'm going to have 3 H's around it. Doesn't matter if one was on top and the side, doesn't matter. And I'm going to connect them all at least with 1 bond like we did with CO2. So that shows me 2, 4, 6 valence electrons. We need 8. Well, hydrogen is happy because it's got 2. This hydrogen's happy with 2. That hydrogen's happy with 2. We're not doing any double bonds anywhere because hydrogen can only hold 2 to be like neon. But nitrogen, if we look, nitrogen only has 2, 4, 6. It needs 8. So we need to draw a lone pair on the top of nitrogen. This would be our Lewis structure for NH3. It would have 3 bonding pairs and 1 lone pair for a total of 8 electrons. Let's draw the Lewis structure of chloroform, CHCl3. That's a compound once used as an anesthetic. Well, here we're told the C, again, the first atom listed is our central atom. Let's do our valence electron count. I've got a carbon that has 4 electrons, an H that has 1, and 3 chlorines. Each chlorine has 7 valence electrons, so 21 plus 1 plus 4 gives us 26 electrons that we need to have in this compound. All right, so I'm going to have C as my central atom. I'm going to put an H somewhere, doesn't matter where, and 3 chlorines around it, Cl, Cl, and Cl. If we all had a single bond in between these guys, that would be 2, 4, 6, 8. 8 electrons. We are far from our 26. Let's see if everybody has 8. Or 2, like hydrogen. Hydrogen is happy, it has 2. Carbon has 2, 4, 6, 8. The central carbon is happy, it's full at 8. But the top chlorine only has 2 electrons around it. So let's fill it up so it has an octet. 2, 3, 4, 5, 6, 7, 8. Let's fill up this chlorine. 3, 4, 5, 6, 7, 8. Let's fill up this chlorine. Now let's do an electron count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. All right, we hit our 26 electrons, and we should match with this. Why don't you pause the video here and see if you can draw the electron dot structure for thionyl chloride, SOCl2, which is a reagent used in organic chemistry. Pause the video here and see if you can do that. Sulfur is our central atom. It is the lowest electronegativity. It's further left and down than oxygen and chlorine. Let's do our valence electron count. Sulfur, there's 6 electrons for sulfur and there's only 1 of them. There's 6 electrons for oxygen and there's 1 of them. And there's 2 chlorines, so 2 times 7 valence electrons for each chlorine. So there should be 26 electrons in this compound. We've got our S as our middle atom, and then an O and 2 Cl's. Again, it doesn't matter if you would have had S, O, Cl, Cl. Doesn't matter how that's arranged. Just by having 1 bond, 1 bond, 1 bond, that's only 6 electrons. We've got to show 26 electrons though. So let's fill in around those atoms to give each one of those 8. So oxygen is happy here. It's got 8. Chlorine's got 8. That chlorine has 8. But if I look, that's only 8, 16, 24. I need 2 more electrons. And my sulfur is not happy because sulfur only has 2, 4, 6. So we have to put 2 more on sulfur to give it that octet. And that would give me 26 electrons. Let's try this one. Methyl chloride, which is CH3Cl. Let's try H2O2. And that H2O2, 2 O's have a bond connected together. And NH2OH, and there's an NO bond. Let's set those up. Let's try, I'll help you get it started. CH3Cl, CH, H, that's 3 H's and a Cl. Now do your valence electron count. This H2O2 is said there was an O bond, so that's our 2 O's, and then we have 2 H's. I'm just going to put an H over here and an H over here. Do your electron count. And then we have NH2OH, and that said that was an NO bond. So that's an N, that's our O, so we have 3 H's to put around it. 1, 2, 3. See if you can figure out where the rest of the electrons go. When I did my electron count, I got 14 electrons for each one of those 3 compounds. Let's see how they all go. We're going to have a bond between each of the carbon, hydrogens, and chlorine. So carbon is happy with 8. Each of those hydrogens is happy with 2, but that chlorine, that top chlorine, only has 2. So we've got so far 2, 4, 6, 8, 9, 10, 11, 12, 13, 14. This guy is done. Let's look at our hydrogen peroxide here. This hydrogen is happy with 2, that hydrogen is happy with 2, but each O only has 2, 4, 2, 4. So we need 5, 6, 7, 8, 5, 6, 7, 8. How many is that? 2, 4, 6, 8, 10, 12, 14, and we are done there. And if you drew this O with an H up here and an H down here, that is fine. As long as, again, each O has 8 electrons around it. Our 14 electrons down here, we've got 2, 4, 6, 8. This nitrogen only has 2, 4, 6, so we need 2 more on the nitrogen. This oxygen, 2, 4, we need 5, 6, 7, 8. Let's double check. Do we have 14? 2, 4, 6, 8, 10, 12, 14 electrons. Here we go. Can you pause here and draw formaldehyde? This one might have been a little tricky for you. When you did your valence electron count, we've got 4 for carbon, 2 hydrogens, so 2 times 1, which is 2, and an oxygen, which is 6. So add those up, 12 electrons we have to account for. Let's draw it. Let's put a C, we've got an H around it, a second H, and an O. So far we have 2, 4, 6. Let's start adding electrons because oxygen is not happy. Oxygen only has 2. And carbon isn't happy because it only has 6. So we can do 7, 8, 9, 10, 11, 12. This oxygen is now happy because it has 1, 2, 3, 4, 5, 6, 7, 8. This hydrogen's happy, it has 2. That hydrogen's happy, it has 2. But the only problem is carbon is not happy. Carbon only has the 2, the 4, the 6. It really wants 8. So let's just take 2 from oxygen and share it with this carbon and form a double bond right there. Then I have when oxygen then just has 2 lone pairs around it. Let's double check to see if everyone's happy now. Hydrogen's happy, hydrogen's happy. This carbon has 2, 4, 6, 8 now. And this oxygen has 1, 2, 3, 4, 5, 6, 7, 8. And let's double check to make sure that we have 12 electrons. 2, 4, 6, 8, 10, 12. That is our structure. Let's draw carbon monoxide. See if you can figure that one out. I did my electron count, 4 from carbon, 6 plus oxygen, so we have 10 electrons. Let's do carbon bonded to oxygen. That accounts for 2. Let's get carbon to be happy. So 3, 4, 5, 6, 7, 8, 9, 10. Okay, there are 10 electrons in that structure now, but we can't be done. Carbon's happy, sure. Carbon has 2, 4, 6, 8. But what's wrong with oxygen? It only has 2, 4. We need oxygen to have 8. So let's take 2 from carbon and share that. That would be 6. Let's take 2 more and share that to give it 8. Let's see what that leaves us with. A triple bond to an oxygen. Oxygen would have a lone pair. Carbon would have a lone pair. Let's double check our counts. Let's look at carbon first. 2, 4, 6, 8. Let's look at oxygen next. Oxygen has 1, 2, 3, 4, 5, 6, 7, 8. And now let's do a total electron count. Make sure we have 10. 2, 4, 6, 8, 9, 10. There we go. Pause the video here to see if you can do the chlorate ion and the nitronium ion. This is a little bit trickier with your electron count. I'll help you with the chlorate. Cl, we're going to have 7 valence electrons. Each oxygen is 6, so 6 times 3 will be 18. And then with a -1 charge, that means it gained an electron, so add an extra electron. If it's a positive charge, we're going to subtract an electron. See if you can get started on those. Let's see how you did. I have a total electron count of 26. I've got my Cl, and I'm going to put 3 O's around it. This chlorine has 2, 4, 6. I'm just going to put 7, 8. And then I'm going to fill each oxygen to give it 8. So far, I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 22, 24, 26. And I think everybody's happy. We don't need any double bonds. Each oxygen has 8. That chlorine has 8. We should have 26 total, and we have this overall -1 charge. Let's look at nitronium. Nitrogen has 5 outermost electrons. There are 2 oxygens, so 2 times 6, and it's a +1 charge, so it lost an electron, so I'm going to -1. 5 plus 12 minus 1 should be 16 electrons. Let's look at N with an O and an O, NO2. And this is overall going to be a +1 ion. And I'm going to start adding electrons to get 16. So we have 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There are the 16 electrons. This bottom O is happy, it has 8. This nitrogen is happy, it has 8, but this oxygen only has 1, 2, 3, 4. We're going to need to share 5, 6, and we're going to need to share again 7, 8. So I'm going to rewrite that. We could have N triple bonded to an O that has 2 electrons here, and then a single bond to another O. But let me ask you, why would this N triple bond to one O and only single bond to the other O? It could also take, this oxygen could take those 2 electrons and share with this nitrogen as well. That would leave me with only a double bond to one oxygen and a double bond to the other oxygen. Let's check our atom count. This nitrogen now has 2, 4, 6, 8. This oxygen has 2, 4, 5, 6, 7, 8. This oxygen, 5, 6, 7, 8. And notice, do we still have 16? 2, 4, 6, 8, 10, 12, 14, 16. There's a couple different ways we could draw this. We could draw it like that. We could also draw the triple bond on the left side and a single bond on the right. Or we could have 2 double bonds. We're going to learn more about that in the next section when we talk about resonance. Pause the video here to draw ammonium, NO+, and SO4, 2-. Did you get these structures? Double check. Pause the video here to make carbon tetrachloride and nitrogen trifluoride. There is your CCl4, and there is your NF3. Draw the structures for CH3OH, which is methanol, and hydroxylamine, H2NOH. In each molecule, the central carbon or nitrogen atom is bonded to hydrogen atoms and an oxygen. Did you get this for your CH3OH? And for your H2NOH. And now we have some join-ins. Which of the following is a correct Lewis structure? Hopefully you wrote number 2. What's wrong with number 1? Nitrogen only has 6 electrons around it, not 8. Number 3, the hydrogens are happy, but this oxygen needs 4 more electrons to have an octet. And number 4, hydrogen's happy, but fluorine only has 6 electrons around it. 2, 4, 6, not an octet. Which is not a correct Lewis dot structure? That'd be this guy. This middle nitrogen would have 2, 4, 6, 8, 10 electrons. Which of the following is not correct? It would be this guy. Nitrogen has 5 electrons, oxygen has 6, and if it's a -1 charge, we're going to add 1, so that'd be 12 electrons. 2, 4, 6, 8, 10. There's only 10 here. Which one of these is not correct? It would be number 4. We do not have a correct electron count. And sulfur is not happy. It needs 2 more. The last 2 slides of this section, one we're going to look at isoelectronic species. And that means that these structures are similar in that they each have 2 atoms. So we have N and O, N and N, C and O, C and N. So there's 2 atoms and the same total number of valence electrons. Each one of these has 10. If we added up nitrogen, which is 5, oxygen, which is 6, but it's a +1 charge, so we subtract 1, that's 10. Each nitrogen is 5, so 5 plus 5 is 10. Carbon plus oxygen, 6 plus 4 is 10. Carbon and nitrogen with a -1 charge would be 10. So isoelectronic, meaning that they have the same number of electrons, which leads to similar Lewis structures for each molecule or ion. The 2 atoms are linked with a triple bond. With 3 bonding pairs and 1 lone pair, each atom has an octet of an electron. When we have carbon-based compounds, that just means that we have organic. Organic just means carbon. Let's say I have C3H6. There are only 2 ways to arrange 3 carbon atoms. This is the only time that you will have, let's say, a circular, or this is a triangle, but when we have atoms connected, that's not in a structure like this, or linear, or in like a T-shaped. We can have a circular or triangular structure when I have carbon atoms. And in this case, if I make this triangle arrangement, I can have CCC. Keep in mind, I gotta now have 6 hydrogens, and we know each carbon can have 4 bonds, and off of, let's see, this bottom left carbon, if there's a bond to that and a bond to that carbon, that's 2, so we need 2 more H's off of each one, so that would be 6 hydrogens. If I had 6 hydrogens off of my linear structure, 1, 2, 3, 4, 5, 6. Notice that my end carbons are not happy because there's only 3 bonds on each of those end carbons. And if I did my electron count, it would not align. I would need to have a double bond for all the carbons to be happy. So this one would take a little bit more work to figure out the electron count and have that double bond.